So we come to the last part of this chapter, and this section is called free fall. Work on this was done by this great man, this great physicist called Galileo Galilei in Italy. And you might have heard something about this Leaning Tower of Pisa and his experiments by throwing two balls down, seeing whether they land on the ground at the same time or not. Okay, so he worked on several things. This is around 1600s, and we are in particular going to talk about free fall, okay, amongst all these things that he worked on. Essentially, we call a motion free fall when an object is falling under the influence of gravity alone. Okay, so it doesn't matter how it starts the motion. Like you could throw it upwards, or you could just drop it downwards. You could push it down with a certain velocity, or you could throw it at a certain angle. But it needs to be moving under the influence of gravity alone. And we're going to look at just the vertical motions because we're doing one dimension. So we're going to let it fall in one direction, which is going to be the y direction this time. So we can use all our kinematic equations. Remember, we had 3 and 1 related to the position as the average velocity times time. Those are our kinematic equations. We're going to use the same equations, but everywhere that we have delta x, we can write it as delta y because our motion is in the y direction and our acceleration is in the y direction and the velocities are all going to be in the y direction, okay, only. So in that y direction, if you're near the surface of the Earth, then the strongest and only acceleration acting on you is the acceleration due to the Earth's gravitational pull. It's called acceleration due to gravity, and it's represented by this lowercase g. Okay? So we're going to assume that we are close to the Earth, and this is the only acceleration. Symbolized by g, its value is exactly 9.8 meters per second squared. There's a slight variation in this between the equator and the poles, and it's also different at different elevations. But we're going to say that it's close enough to 9.8 to take this as a constant. Okay? Sometimes we might have that as 9.81 meters per second squared. So the question or the question paper will tell you whether to take 9.8 or 9.81. And you must take exactly the value given to you. For an estimate, you can use 10 meters per second squared, okay, because that's pretty close to 10 if you round it to 2 places. Okay. It's always going to be directed towards the center of the Earth. So since we're on the surface of the Earth, we're going to say that center is downwards. And so we're going to put a negative symbol to show the direction, because remember, it's a vector quantity, acceleration. So this is the magnitude, 9.8, okay? And the direction is always towards the center of the Earth, okay? Typically, when we do these questions, we're gonna neglect air resistance, okay? And we're gonna neglect all those small changes in g that I talked about, okay? With vertical distance or with distance from the equator. So we're just gonna take it as a constant. Okay, so here I've taken g as negative 9.8 meters per second squared. Just one word of caution here. Beware of putting double negatives, okay? So if you've already taken that direction into account, then you have put your negative sign. You do not put it again in the equation, okay? Say I have this ball here and I just let go of it, then it's going to fall downwards, right? Because the Earth is pulling it. So if I just let go, that means it's starting from rest and its initial velocity is 0. It's going to experience free fall downwards with this acceleration. So its velocity is downwards, its acceleration is downwards. What do we expect? We expect that the ball is going to be speeding up until it hits something, such as the ground. So when it's at its fastest, it's going to hit the ground, yeah? Let's consider the case when we actually throw the ball upwards. This time we throw the ball upwards, it rises to a certain height, and then it comes back down. So the velocity is initially upwards, and finally it's downwards. Going from positive to negative, it must go through 0. That 0 exactly happens at that highest point. So when the motion reverses, we always have to go through a 0 velocity, And that's going to happen at the highest point. So we already know something about the highest point. We know the velocity at that point. We're going to assume that there is no curve between here, that this is a straight line, and we've just shown you this in order for you to see better that it goes up and it comes down. But it goes up and down in the same straight line because we're just taking one-dimensional motion, okay? Right from the start, its velocity is upwards because you threw it upwards, right? So it has some positive velocity, but the only acceleration it has is this acceleration due to gravity, which is downwards. So at the start, it's starting with its highest positive velocity. It is losing speed. So it has smaller and smaller magnitude of positive velocity till it comes to a stop. And now it has a negative velocity and it has a negative acceleration. They are both again in the same direction now. So the object is speeding up, coming down faster and faster till it maybe hits the ground. Okay, so as it goes upwards, it is slowing down to zero. As it comes downwards, it is speeding up. Sometimes you'll have questions where this object is launched from on top of a building or a cliff. So you might have a symmetrical portion of the object going up and coming back down from where it was launched. And then you might have a further portion coming back down this given height, right? Or the height might be asked for. So you sometimes split the motion into this symmetrical part and then the rest of it. Another way of doing it is to split the motion into all the upward motion and then all the downward motion. Okay, so that's just talking about it. We'll do some examples in a minute. Okay, so this is a detailed example and we're going to work it out on the whiteboard like we did last time. I'm not going to work out every part. I'm going to give you a flavor and then you need to work it out and you need to plot some graphs here. So let's read the question together. A person standing at the edge of a high cliff throws a rock straight up with an initial velocity of 13 meters per second. The rock misses the edge of the cliff as it falls back to earth. So this looks very much, when you sketch it, looks very much like just the last slide where there's somebody standing on top of a building. Here he's standing on top of a cliff. He throws it up and the object comes down. Both are the same straight line. Okay, one dimension. Upward being positive, downward being negative. Okay. Calculate the maximum height reached and how long it takes to attain it. Okay, so we already know something about the maximum height. Think about what that was. That was that the velocity is going to be zero at the maximum height. Yeah? And we need to find the time corresponding to when the velocity is zero. Okay. We also want to find the position and velocity of the rock at 1, 2, and 3 seconds after it's thrown, neglecting the effects of air resistance. So we're now going to start. We've read through the problem. What's the next thing we need to do? We need to sketch our problem, right? We need to label as many things as possible. We need to have our origin, our one dimension, write down what we don't know, write down what we do know, try to find a relationship between them, maybe using kinematic equations, and see what we can solve. Okay, so we're going to use the whiteboard to do that, and you're going to go to group work 2B to find that. Thank you. Stop here. Let me just also talk you through the solution that we're going to see after. Okay, now I'm going to put that separately.